what if I told you that ancient engineers, without electricity or computer modeling, built structures faster than we do today with our powerful machines? It sounds incredible, but Roman roads built 2 millennia ago still serve as the foundation for modern European highways. Amphitheaters that could hold tens of thousands of spectators were built in a matter of years, not decades. The secret lies not in magic, but in an ingenious system, standardization, and organization of labor, perfected to the absolute. The Romans turned construction into a mechanism as well-oiled as their legendary army. Watch the video to the end to find out how the Romans managed to build fully fortified military camps for entire legions in just a few hours, and why their concrete in some cases surpasses modern equivalents. I will reveal the most closely guarded secret of Roman construction, and it is not some secret material, but one word: standardization. It was this concept, taken to the extreme, that allowed Rome to build so quickly and so much. Everything from bricks and pipes to road widths and camp stake sizes was standardized. This meant that materials produced in Gaul could be used in Syria without any problems. Engineers did not have to reinvent the wheel every time. They worked with a set of proven and approved solutions. This system began with fundamental measurements that every legionnaire and builder knew: the Roman foot, palm, elbow, and of course the famous passus, or double step, which formed the basis for measuring miles. When every worker on site operates with the same precise units, the speed of coordination increases many times over. There was no need to waste time coordinating plans drawn up by different craftsmen using different systems. An architect could send a drawing to the other end of the empire, confident that it would be understood correctly. Take Roman bricks, for example. Unlike many other cultures, the Romans standardized not only the shape, but also the dimensions of several basic types of bricks. This allowed for their mass, almost industrial production in special factories. When legions arrived at a new location, they could immediately access ready-made building blocks. This eliminated one of the most labor-intensive stages, the extraction and processing of stone on site. Standardization also affected the tools that each legionnaire carried. The famous dolabra, a hybrid of a pickaxe and an axe, was a universal tool, identical for the entire army. Each soldier carried not only weapons, but also construction equipment. This meant that if necessary, a centurion could instantly turn his combat unit into an effective construction brigade. There was no need to wait for shovels or pickaxes to be delivered. Every soldier already had them. Roman engineers created entire catalogs of standard architectural elements. They did not need to recalculate the arch of a bridge or the vault of a basilica each time. There were proven proportions and methods that guaranteed strength and durability. The architect essentially worked as a designer, assembling a project from ready-made, reliable, and interchangeable modules. This greatly reduced the risk of error and accelerated the design process. This modularity was evident in everything from the layout of military camps to the construction of aqueducts. Each camp had a standard rectangular shape with the same layout of streets and gates. A soldier arriving at any camp from Britain to Egypt could find his centurion's tent or praetorium with his eyes closed. This predictability saved a tremendous amount of time in deployment and construction. Even something as complex as water pipes was standardized. They were made of lead by rolling sheets into pipes and soldering the seams. There were about 15 standard diameters, each with its own name. This allowed engineers to accurately calculate the capacity of aqueducts in urban networks. Repairing such networks was also simplified, as the damaged section could be easily replaced with a standard section. Roman law also supported this system by protecting engineering plans and standards. Construction contracts were incredibly detailed, describing every material and every stage of work. This created a uniform legal and technical field throughout the empire. A contractor in Spain built a bridge according to the same rules and standards as a contractor in Asia Minor. The speed of Roman construction was a direct result of this standardization. When you have standard materials, standard tools, standard plans, and a workforce trained to a uniform standard, you eliminate most of the delays. The process becomes a conveyor belt where each stage is predictable and well-oiled. It was this systematic approach, rather than any single invention, that was the main Roman miracle. This standardization was a real invisible revolution, thousands of years ahead of its time. It became the foundation on which the entire power of Roman engineering grew. We are very interested in hearing your point of view. What do you think is the direct heir to this total Roman standardization in the modern world? Write your opinion in the comments. And of course, don't forget to subscribe to our channel so you don't miss our next studies. Are you ready to learn the truth about Roman legionaries that overturns the usual image of a soldier? For most of us, a legionary is a warrior in armor with a sword and shield. But the truth is that he was as much an engineer and builder as he was a fighter. Every soldier was trained not only to fight, but also to dig, build, lay roads, and erect bridges. This versatility was one of Rome's main strengths. Training for new recruits in the Roman army included not only marching and weaponry. A significant part of the time was devoted to engineering work. Soldiers were taught to dig trenches, build ramparts, install palisades, and use surveying instruments. They practiced masonry and carpentry. As a result, the army was not just a fighting force, but a mobile corps of highly skilled workers. Each legion had a whole staff of immunes, specialists who were exempt from daily duties in order to perform technical tasks. Among them were surveyors, carpenters, masons, blacksmiths, and engineer architects. These specialists formed the core around which thousands of ordinary legionnaires could be instantly organized to carry out the most complex projects. This engineering corps was commanded by the prefect of the camp, one of the highest-ranking officers in the legion. A legionnaire's equipment spoke for itself. In addition to a sword, dagger, and armor, each soldier carried an impressive set of tools. It necessarily included a delabra, pickaxe axe, a shovel or hoe, as well as two heavy, double-edged stakes known as sudes. These stakes were used to erect a palisade on the camp rampart. Thus, the legion always had both labor and tools at its disposal. This system allowed the Roman army to move with incredible speed and safety. At the end of each day's march, no matter how tired the soldiers were, the legion would stop and build a fully fortified camp. This was not just a rest stop, but the construction of a real fortress. Thousands of people worked in unison, digging a moat, filling the rampart, and installing a palisade on it from the very piles they carried with them. The entire process of building the camp was automated and took only a few hours. While one part of the legion stood guard, the other two parts worked. Surveyors quickly marked out the standard rectangle of the camp, and soldiers, divided into squads, each performed their own task. This incredible speed and organization deprived the enemy of any chance of a surprise night attack. The legions were not only builders of temporary camps, but also creators of long-term infrastructure. It was the army that built the famous Roman roads that connected the new provinces to the heart of the empire. Soldiers were the main labor force on these projects. They cleared the land, removed soil, laid a multi-layered road base, and paved the top layer. It was hard work, but it ensured the rapid movement of troops. Bridge construction was another task that army engineers mastered. Caesar's famous bridge across the Rhine was built in just 10 days. This demonstrated to the Germanic tribes not so much the military power of Rome as its engineering prowess. Legionnaires drove piles into the bottom of the fast-flowing river, created sturdy supports, and laid the decking using pre-prepared materials. Even large civilian structures, such as aqueducts and amphitheaters, were often built with the direct participation of the legions. In peacetime, when the army was not engaged in active combat, the soldiers needed something to occupy themselves with. Construction projects were the ideal solution. They maintained discipline, honed engineering skills, and created valuable infrastructure that strengthened Rome's presence in the region. This dual function of the army, to fight and to build, was a brilliant organizational solution. Rome had at its disposal the largest, most disciplined, and most skilled construction organization in the ancient world. When it was necessary to implement a large-scale project, the emperor did not need to look for contractors. All he had to do was give the order to the legion. This system turned the army into a mobile construction company capable of changing any landscape. But what if I told you that their main secret was not in the people, but in the material they invented? In the next chapter, we will reveal the secret of Roman concrete, which still cannot be surpassed. What many modern engineers don't talk about, Roman concrete really was better in many ways. This is not an exaggeration, but a fact confirmed by research. This material, known as opus cementitium, was a true technological revolution that allowed Rome to build faster, higher, stronger, and on a scale that was previously unimaginable. It was not just a mortar, but the first structural concrete in human history. The main secret of this material lay in its unique binding agent. The Romans discovered that a mixture of lime and a special volcanic ash, which they called pozzolana, created an incredibly strong mortar. This ash, mined mainly in the area around Pozzuoli near Vesuvius, had unique chemical properties. When mixed with lime and water, it reacted to form new, extremely durable mineral compounds. Unlike simple lime mortar, which hardens in the air, Roman concrete was hydraulic. This meant that it could set and gain strength even underwater. This property was an absolute breakthrough. It allowed the Romans to build massive bridge supports directly in riverbeds, erect strong breakwaters, and construct entire artificial harbors. Modern Portland cement, the basis of our concrete, is essentially an attempt to recreate the properties of this ancient material. The manufacturing process was simple and effective. Workers mixed lime, pozzolan, and water to obtain a thick solution. Then they prepared a filler called cementa. These were pieces of broken stone, crushed stone, gravel, or even fragments of old ceramics. Wooden formwork was erected on the construction site, replicating the shape of the future wall or arch. The mortar was poured into this form in layers, and the aggregate was laid. The result was not just masonry, but a monolithic structure. After the mortar hardened, the entire mass turned into a single artificial stone. This was much faster than the laborious process of fitting and laying massive stone blocks. In addition, this method required much less skilled labor. The main work of mixing and pouring could be done by ordinary workers, rather than expensive master masons. It was opus cementitium that allowed Roman architects to revolutionize forms. They were able to move away from a simple beam system and begin to actively use arches, vaults, and domes. Concrete was ideal for creating curved surfaces. The most striking example is the dome of the Pantheon in Rome, which remains the largest unreinforced concrete dome in the world. Its construction would have been impossible without this plastic and durable material. The strength of Roman concrete only increased over time. Modern research has shown that thanks to pozzolan, chemical reactions continued in the structure of the material, making it denser and more resistant to destruction. Seawater, which is destructive to modern concrete, reacted with Roman concrete to form new crystals that essentially healed microcracks. This is why Roman port structures have stood in the aggressive marine environment for more than 2,000 years. The speed of construction using concrete was astonishing. Instead of carving and lifting huge stones, workers could simply pour the material into a mold. This made it possible to erect such gigantic structures as the Coliseum in record time. The walls of this amphitheater are a complex system of concrete vaults and arches faced with stone. Without concrete, this project would have taken decades to complete. The availability of materials also played a role. Although the best pozzolan was found near Vesuvius, the Romans learned to find or create its equivalents in other provinces. They used crushed brick or ceramics as artificial pozzolan, which also provided a good hydraulic effect. This allowed concrete technologies to be applied throughout the empire, adapting them to local resources. This technology allowed Rome to literally pour its empire into shape, rather than simply laying it out in stone. It was the ideal material for rapid and mass construction, cheap to produce, requiring no highly skilled workers, and incredibly durable. If you are also amazed by this engineering magic, which was ahead of its time by millennia, please support our channel with a like. And don't forget to subscribe so you don't miss new videos about ancient Rome. What if I showed you a time machine that still works today? It's the Roman road. The famous phrase, "all roads lead to Rome," was not just a metaphor, but a literal description of reality. The Romans created the most advanced and extensive road network in the ancient world, which became the backbone of their empire. But what is most striking is not only their durability, but also the speed with which they were built. Road construction was primarily a military task. Roads were needed to quickly move legions to any point in the empire. Therefore, the army was responsible for their construction, and the Legionaries were the main builders. Speed was critically important. A new road meant control over new territory. Therefore, the construction process was well organized, standardized, and incredibly efficient. It all started with surveyors, or grammatics. These specialists used a simple but ingenious tool called a groma. It was a pole with a cross at the top, from which plumb lines hung at the four ends. With the help of the grammata, engineers could lay perfectly straight lines for many kilometers, ignoring minor obstacles. Roman roads are famous for their straightness. They ran straight through hills and swamps. Once the route had been marked out, the legionaries got to work. First, they dug a wide and fairly deep trench, called a fossa. The depth could reach up to 1.5 meters. This was done in order to remove the soft topsoil and reach the solid foundation. In addition, this immediately solved the problem of drainage. Roman engineers understood perfectly well that the main enemy of the road was water. Then began the process of laying a multi-layered pie, which ensured legendary strength. A layer of statumen, large, roughly hewn stones, was laid at the bottom of the trench. This layer served as a foundation and distributed the load. The gaps between the stones could be filled with sand or gravel. The thickness of this layer ensured the stability of the entire structure. The next layer, the rudus, was laid on top of the foundation. It consisted of smaller stones, rubble, or broken bricks mixed with clay or lime. This layer was thinner, but it was carefully compacted to create a dense and waterproof base. Legionnaires used heavy hand tampers for this purpose. The work was exhausting, but the fate of the road depended on its quality. The third layer, the nucleus, was essentially concrete. It consisted of fine gravel, sand, and hot lime, sometimes with the addition of pozzolan. This mixture was laid hot, and as it hardened, it turned into a solid, monolithic base. This layer was the final barrier to water and served as an ideal cushion for the top layer. Finally, the top layer, the pavement, or summum dorsum. On the most important roads, such as the Appian Way, it was made of large, polygonal stone slabs. These slabs were so carefully fitted together that it was difficult to insert a knife blade between them. The surface of the road was made slightly convex, humpbacked, so that rainwater would flow into drainage ditches, which were always laid on both sides. The speed of construction was due to the army's organization. The legion, divided into centuries and maniples, worked as a single mechanism. Some felled trees and cleared the forest, others dug trenches, others brought stones, and still others laid the layers. The work continued from dawn to dusk. In this way, the legion could build dozens of kilometers of first-class roads in a single season. This road network was a marvel of logistics. Every Roman mile, about 1,080 meters, there was a milliarium, a stone pillar indicating the distance to Rome or the nearest large city. Along the roads, mansiones were built, state-owned inns where couriers and officials could change horses and rest. Imagine being able to travel hundreds of kilometers on a perfectly straight, all-weather road. What modern invention, in your opinion, can compare to this in terms of significance? But to build these roads, materials were needed. In the next chapter, we will learn how the Romans organized the most extensive logistics network of the ancient world. The success of any grand construction project, whether today or 2,000 years ago, depends not only on brilliant engineers, but also on the boring but vital task of logistics. The Romans were absolute geniuses of logistics. They understood that building an amphitheater or aqueduct was primarily a task of timely delivery of millions of tons of materials and organizing thousands of workers on a single site. And in this, they were unmatched. The foundation of Roman construction logistics was the state. Most large projects were state-owned, financed from the imperial treasury, and supervised by senior officials. This gave them access to virtually unlimited resources. The state owned huge quarries, forests, and brick factories throughout the empire. When the emperor decided to build something, he did not look for suppliers. He simply gave the order. Transportation was the main headache. The cheapest and fastest way was by water. The Romans actively used all navigable rivers, and the Mediterranean Sea was, in fact, an internal Roman lake. Huge barges and merchant ships transported marble from Greece, granite from Egypt, and timber from Gaul. Special canals were often built to deliver materials deep into the mainland. Where waterways were inaccessible, oxen transport came into play. Thousands of oxen slowly pulled carts loaded with stone blocks along those same Roman roads. It was slow and very expensive. It is estimated that transporting a cartload of grain 100 miles by land doubled its cost. Therefore, engineers always tried to locate quarries and factories as close as possible to waterways or directly to the construction site. For projects such as the Coliseum, an entire industrial area grew up around the construction site. Huge warehouses were built to store lime, sand, and pozzolan. Workshops were set up where masons cut blocks and carpenters prepared formwork and scaffolding elements. Thousands of people worked on the site, and they had to be fed and housed every day. It was a very difficult organizational task. The Romans masterfully managed these flows. They drew up detailed delivery schedules. For example, the quarries in Carrara, where the famous marble was mined, worked in strict accordance with orders from Rome. Blocks of the required size were cut, marked, and sent to the port. In Rome, they were received, delivered to the site, and placed in their exact location in the structure. This required incredible coordination. Brick factories were another example of Roman efficiency. They often belonged to legions or even members of the imperial family. Special stamps were placed on the bricks, which today allow us to trace which legion or workshop produced them. It was a system of quality control and accounting. Mass production of standard bricks ensured a constant supply of material for any construction project. The organization of the workforce was also top-notch. Projects were broken down into many small sections and tasks. Different teams worked in parallel. For example, during the construction of an aqueduct, one team could dig a tunnel in a mountain, another could build an arched bridge across a valley, and a third could build a distribution reservoir in the city. They all worked according to a single plan and under the direction of one chief engineer. Project management was strict. There were special officials, curators, who were responsible for specific objects. For example, the curator of water pipes. They monitored the expenditure of funds, compliance with deadlines, and the quality of work. Contractors working for the state bore serious responsibility. All this created a system in which speed and efficiency were the top priorities. The Roman logistics machine was the invisible engine that allowed the empire to expand and build so quickly. It was based on state control of resources, a developed transport network, and iron army discipline. Without this system, even brilliant engineers and unique concrete could not have created the wonders we still see today. Guess what happened every night in the Roman army that terrified all its enemies? Every evening, after a long day's march, the Roman legion did not simply pitch tents. In a matter of hours, it erected a fully fortified fortress, or castrum, from scratch. This ability to create an instant city anywhere was one of Rome's greatest tactical advantages and a true engineering marvel. This practice was not optional, but mandatory. The rule was ironclad. The legion did not spend the night in open terrain. No matter how tired the soldiers were or how safe the area seemed, work began immediately. This was the quintessence of Roman discipline and foresight. They did not give the enemy a single chance for a surprise attack. The process was perfected to the point of absolute automatism. Even before the main forces arrived, a detachment of surveyors, or grammatici, was sent ahead. They chose a suitable location, usually on high ground, with access to water and wood. Then, using thunder, they quickly marked out a standard, rectangular camp plan on the ground. They stuck flags of different colors into the ground, marking the location of the praetorium, the centurions' tents, and the main streets. As soon as the legion arrived, it was divided into 3 parts. One part, fully armed, formed a defensive perimeter, ready to repel any attack. The other 2 parts immediately set to work. Every soldier knew exactly what to do. There was no fuss or unnecessary commands. It was a well-oiled machine, with thousands of people moving as one. The first task was to dig a trench, or fossa. Thousands of legionnaires used their shovels and delabras to throw earth inside the marked perimeter. This earth was immediately used to form a rampart, or agger. They worked in shifts, quickly passing tools from one to another. The speed was incredible. A deep ditch and a high rampart grew before our very eyes. At the same time, the 2 stakes, sudes, that each soldier carried were put to use. These stakes were not just sticks. They had a complex shape with pointed ends and a narrowing in the middle, which allowed them to be fastened very tightly together. The soldiers placed them on top of the rampart, creating a vallum, a strong, thorny palisade that was almost impossible to get through. Inside the camp, everything was also perfectly organized. The streets, the Cardo and Decumanus, crossed at right angles. Each cohort, each centuria, and each contubernium, tent 8, had its own strictly defined place. The soldiers pitched their leather tents, which they also carried with them. The camp was a smaller, standardized copy of Rome itself. This standardization also had a psychological effect. Soldiers, thousands of kilometers from home, in enemy territory, found themselves in a familiar and safe environment every evening. This reduced stress and maintained morale. They knew where to find their officer, where the food supply was, and where their place in the ranks was in case of an alarm. The entire operation of setting up a camp for a full legion, a moat, a rampart, a palisade, 4 gates, and thousands of tents, took 3 to 6 hours. By sunset, the army was safely sheltered behind the walls of a fortress that had been unimaginable in that place just that morning. In the morning, the camp was dismantled just as quickly, and the legion set out on its march, leaving behind only an empty rectangle of earthen fortifications. This ability to create an instant city gave the legions an unmatched strategic advantage. They could operate in any territory without being tied to cities or bases. What modern military practice do you think is comparable to this in terms of organization and speed? But building camps was only one of their tasks. In the next chapter, we will talk about how they delivered water to these cities using aqueducts. Rome was a city obsessed with water. Public baths, or thermae, were the center of social life. Fountains adorned the squares, and wealthy citizens had running water in their homes. To meet this demand, Roman engineers created one of their most impressive creations, aqueducts. These structures delivered clean spring water to cities, sometimes tens of kilometers away, and did so with remarkable precision. The secret of the aqueduct was gravity. The entire system was, in essence, a long, slightly sloping channel through which water flowed by gravity from its source in the mountains to the city's distribution reservoir. The engineer's task was to find a source located high enough and to lay a route with a perfect, very gentle slope. An error in calculations of a fraction of a degree could render the entire multi-kilometer project useless. To calculate the slope, the Romans used a horobatus. It was a long, about 6-meter-long wooden beam with plumb lines and a recess for water on the upper surface. It worked like a modern construction level. Engineers used the horobatus to carefully measure the slope, which had to be constant throughout the entire route. The slope was minimal, sometimes only a few centimeters per kilometer. It was precision work on a landscape scale. Contrary to popular belief, most of the aqueducts were hidden underground. It was both cheaper and safer. Engineers laid spicus, or channels, in trenches or even dug tunnels through mountains. The channel was usually made of stone or concrete and covered on the inside with a special waterproof mortar called opus signinum, made from lime and crushed ceramics. The famous multi-tiered arches we associate with aqueducts were a solution to a specific problem. Crossing a valley or ravine, instead of routing the canal along a long detour, engineers threw it straight across. The construction of arches such as those at Pont du Gard in Gaul was the pinnacle of engineering. They had to be not only strong enough to carry the weight of the canal with water, but also maintain the most precise and continuous slope. The speed of construction was achieved through proven technologies. The arches were erected using wooden centering, temporary frames that supported the stones until the keystone was laid. The Romans were masters of arch construction. This form allowed them to span large distances and save material. Concrete was often used to build arches, which was poured into wooden formwork. In the city, water from the aqueduct flowed into the main distribution reservoir, the Castellum Aquae. It was a monumental structure, often richly decorated. From there, water flowed through a system of lead pipes to public fountains, baths, and private homes. The system was well thought out. The pipes to private villas were higher than those to public fountains. In the event of a drought, the rich were the first to be left without water. not ordinary citizens. Maintaining the aqueducts was a constant task. The channels had to be cleaned of lime deposits, which narrowed the passage over time. For this purpose, there were special inspection shafts and sedimentation tanks where debris and sand settled to the bottom. There was even a special government service, the Cura Aquarium, responsible for maintaining the water pipes in working order. The construction of an aqueduct was an incredibly expensive and complex project, often taking years to complete, but the Romans were willing to incur these costs. They understood that clean water was the basis of hygiene, health, and, ultimately, civilization. The aqueduct was not just an engineering structure, but a symbol of Rome's power over nature and its concern for its citizens. Roman aqueducts are a monument to precise calculation, patience, and incredible perseverance. They demonstrate how a systematic approach and skill made it possible to solve problems that seem difficult even today. Dozens of these ancient waterworks were so well built that some of them, after minor repairs, are still used for water supply today. When we think of Roman engineering, the Coliseum immediately comes to mind. This gigantic amphitheater, officially known as the Flavian Amphitheater, is not only a symbol of Rome, but also the pinnacle of organizational and construction genius. The most striking thing is the speed of its construction. According to various estimates, such a monumental structure was erected in just 8 to 10 years. In our time, the implementation of a similar project would take no less time. The secret to its speed lay in several factors. First, it was a project with unlimited funding and the highest political priority. It was built by the emperors of the Flavian dynasty. Second, ingenious logistics were employed. And third, the Romans used their best technologies: concrete, arches, and standard modules. The location for the construction was not chosen at random. The Coliseum stands on the site of a drained artificial lake that was part of Emperor Nero's Golden House. It was a powerful political move to return to the people the land that Nero had taken for himself. But from an engineering point of view, it was a problem. To support the weight of the gigantic structure, engineers had to lay a massive concrete foundation 13 meters thick. The Colosseum's design is based on the ingenious use of arches and vaults. The entire ellipse consists of 3 tiers of arches that support the rows of seats. This system was not only durable, but also allowed for rapid construction. The work was divided into sectors. Many teams could simultaneously and independently erect their sections of the arches. It was an early form of modular construction. Materials were used wisely. The outer wall and load-bearing columns were made of heavy and durable travertine, which was delivered from quarries in Tivoli. The stone blocks were joined not with mortar, but with huge iron brackets. The internal structures, arches and ceilings that supported the seating were made of lighter tuff and, of course, concrete. The higher up, the lighter the materials. Concrete with pumice was used in the upper arches. The logistics were incredible. Stone, sand, lime, and wood were continuously delivered to the construction site. Tens of thousands of workers labored on the site. Giant wooden cranes called pulley blocks were used to lift heavy stone blocks to great heights. These cranes were powered by people who walked inside a large wheel like squirrels. This system of blocks made it possible to lift loads weighing many tons. But the Colosseum is not only a construction marvel, but also a logistical one. Engineers thought not only about how to build it, but also about how it would be used. A system of 80 entrances, called vomitoria, was designed so that 50,000 spectators could fill the amphitheater in 15 minutes and leave just as quickly. The flow of people was divided so that different social classes would not mix. Beneath the arena lay another complex world, the hypodrome. It was a 2-level system of tunnels, chambers, and lifting mechanisms. With the help of elevators and ramps, scenery, people, and wild animals could be suddenly lifted into the arena. It was a high-tech show controlled from underground. This complex system was built after the main opening, but it demonstrates the highest level of engineering thought. The speed of the Colosseum's construction was the result of a perfect combination of political will, unlimited resources, ingenious engineering solutions, and clear organization of labor. It was not just an amphitheater, but a statement about the power and capabilities of the Roman Empire. It showed that Rome could implement a project of any scale in a time frame that seemed fantastic. The construction of the Coliseum was made possible by thousands of nameless workers and dozens of brilliant engineers. They created not just a building, but the perfect machine for mass entertainment. Every element, from the foundation to the velarium canopy system that protected spectators from the sun, was designed with incredible care. The speed and precision of Roman construction would have been impossible without a set of specialized, yet simple and reliable tools. Roman engineers did not have laser levels or excavators, but their toolbox was perfectly suited for monumental construction. These tools were so successful that many of them remained virtually unchanged until the 19th century. The main tools of the surveyor were the groma and the horabat, which we have already mentioned. The groma was responsible for straight lines and right angles. The horabat was responsible for horizontal levels and precise slopes. There was also a third tool, the diopter. This was a more complex device, something like an early theodolite, which allowed angles and heights to be measured. It was necessary for designing complex structures, such as tunnels or aqueducts. For earthworks, legionnaires and workers used simple but effective tools. The delabra, a hybrid of a pickaxe and an axe, was a universal army tool for cutting and digging. Heavy hoes, spades, and shovels with wooden handles and iron tips. Woven baskets were used to carry earth. It was hard manual labor, but its effectiveness was achieved through mass participation and organization. Iron wedges and hammers were used in quarries. Workers drilled a series of holes in the stone, into which they then drove wooden wedges. These wedges were doused with water. As it swelled, the wood split the stone along a predetermined line with tremendous force. For harder rocks, such as granite, a method of heating and rapid cooling was used. It was slow and laborious work that required a great deal of experience. The mason's tools were the most important ones on the construction site. A set of chisels of various sizes, from heavy scarps for rough work to thin cesties for carving. Heavy iron hammers and wooden mallets. Special trowels and abrasive powders were used to level the surfaces of the stones. Roman masons achieved incredible precision, fitting the blocks so tightly that not even a blade could fit into the seam. Leverages, blocks, and of course, cranes were used to lift loads. The simplest crane consisted of a single inclined beam with a block at the end. But for large projects, such as the Coliseum, a polypterus was used. This was a complex crane with several blocks that provided a multiple gain in strength. It was driven by a squirrel wheel in which 2 to 4 people walked. Such a crane could lift blocks weighing several tons. Carpenters used saws, axes, adzes, and planes very similar to modern ones. They were responsible for the construction of complex wooden structures, scaffolding, formwork for concrete arches, hoops for arches, and roof truss systems. Roman carpenters knew how to create strong and complex joints that could withstand enormous loads. The Romans used folding rulers, compasses, and plumb lines for measuring. The plumb line, or perpendiculum, was the simplest but absolutely indispensable tool for checking the verticality of walls. It was simply a weight on a string. Combined with a square, it allowed for the construction of perfectly straight walls. Roman engineers created a system of tools that perfectly complemented their construction technologies. They did not pursue complexity, but valued reliability, accuracy, and simplicity. Each tool was honed by centuries of practice. It was this pragmatic approach that allowed them to build so much and so well. It is amazing how such monumental structures could be erected with such a seemingly simple set of tools. This proves that the Roman engineer's main tool was his head. He knew how to combine these simple elements to solve the most complex problems. Behind all these technologies, materials, and tools was the main force that built Rome: people. The engineering genius of Rome would have been nothing without its organizational genius. They created the human engine, a labor management system that allowed them to mobilize and coordinate the efforts of tens of thousands of people on a single project. It was this system that was the secret to their incredible speed. At the head of the project was always the architect. This was not just an architect in the modern sense, but a chief engineer, project manager, and designer all rolled into one. He was responsible for everything from the initial design and budget to overseeing construction. Often these were people with military experience, accustomed to discipline and large-scale tasks. Their names, like that of Apollodorus of Damascus, who built Trajan's bridge, went down in history. Below them were the immunes from the legions, specialist engineers, surveyors, and masons. They formed the technical backbone of the army. In civil construction, there were guilds, or collegia, of craftsmen. These were professional unions of carpenters, masons, and plumbers. They kept the secrets of their craft and ensured a high level of skill. The bulk of unskilled labor was performed by legionnaires in peacetime and during military campaigns. A huge number of workers were employed on large civil projects in Rome and other cities. These were free citizens hired on a daily basis for construction work, as well as workers provided under contract. The organization of their labor was the key to speed. The Romans masterfully applied the principle of division of labor. The project was broken down into many small, repetitive operations. One worker dug, another carried soil, a third mixed mortar, and a fourth handed bricks. Each performed a simple operation, but did so quickly and continuously. It was a conveyor belt, organized 1,500 years before Henry Ford. Discipline on the construction site was military-like. The working day was long, from dawn to dusk. Centurions and overseers made sure that the work did not stop. The use of standard tools and materials also contributed to speed. Workers did not need to think or improvise, they simply performed their function in a large mechanism. When building structures such as the Coliseum, a sector method was used. The structure was divided into 4 large sectors, each with its own independent team responsible for building its section from the foundation to the top tier. This introduced an element of competition, but more importantly, it allowed work to be carried out in parallel around the entire perimeter. The Romans also understood the importance of motivation. Legionnaires who built roads or camps did so as part of their service. Civilian workers were paid. Contractors who took on government contracts could either become fabulously wealthy or go bankrupt if they did not meet deadlines and budgets. There was also pride in their work. On many bricks and even lead pipes, we find the names of craftsmen and workshops. This gigantic, well-oiled human resource management machine was Rome's main modern mechanism. They built quickly not because they had excavators, but because they knew how to organize 100 people with shovels like no one else. They turned a mass of people into a unified, coordinated, and incredibly powerful tool. Ultimately, the history of Roman construction is not only a history of concrete and arches, but also a triumph of organization. They proved that with the right system, standardization, and iron discipline, you can move mountains. They didn't just build buildings, they built a civilization. And they did it at a speed that still amazes us today. We can see that Rome's engineering genius lay not in any one secret invention, but in a perfect system. It was a combination of pragmatic thinking, ingenious materials such as hydraulic concrete, and military-style organization of labor. Standardization of everything from bricks to military camp plans allowed them to work at assembly line speed. The legionnaire, who was both a soldier and an engineer, was the living embodiment of the system. The Romans did not wait for inspiration. They acted according to a proven plan. They built quickly not despite the lack of modern machinery, but thanks to their unique ability to turn thousands of people into a single, well-coordinated mechanism. Their roads, aqueducts, and amphitheaters still stand today, not only as architectural monuments, but also as an eternal reproach to our own era, which despite its incredible technologies, often cannot compare with them in speed, quality, and durability. They built not for decades, but for eternity. What other topics from the history of ancient technology would you like us to cover? Perhaps you are interested in the engineering art of the Incas or the complex mechanisms of ancient Greece. Suggest your ideas for future videos in the comments. And of course, don't forget to subscribe to our channel so you don't miss out on new, amazing discoveries.